function. You just need to try a candidate parameter vector and judge with your expert knowledge, with your experience, if the parameter vector is a reasonable solution. Usually this is done by visual comparison. So now I'm trying to suggest some graphical techniques to perform a visual comparison. And this visual comparison is also useful in this case for the automatic calibration when you finally look at the hydrograph. So you have to get used to judge when the simulation is satisfactory. And there are different graphical techniques that can be used. Let me show you one possibility. Is very simply the graph of observed versus simulated hydrograph. This is very simple. In this case, there is the comparison, which is shown for a modeling experience. Let's forget about these gray lines for now. Let's concentrate on the dotted lines. Dotted means, sorry. Let's concentrate on the graph given by lines and bullet points. Okay? So there is the black one, which is observed, and there is the gray one with gray circles, which is simulated. And you see the comparison. This is a comparison where you can see that you have a percentage error that is close to 50% for the peak, but the low flows are well reproduced. The flood volume is not well reproduced because the gray line is always below or coincident with the black line. If you compute the volume, which means that you compute the area, the integral of these hydrographs, the area below the hydrograph, you see that the gray line has an area that is lower, so the volume is lower. So by looking at this hydrograph, you can realize that you get a fairly good simulation of the low flows, a poor simulation of the peaks, a poor simulation of the volume, a good simulation of the time to peak. We didn't speak of time to peak so far. There are some objective functions that are based on comparing the time to peak. In some cases, it's very important. If you use your model to predict when a flood will arrive, and you are just interested in timing, the model must perform well for the time to peak. Okay? In this case, you get this picture. Basically, it's important that you learn to reason about a comparison, a hydrograph comparison. In this case, if I had to formulate an overall judgment, I would say that the model is not very good, especially if you are interested in the peak. It's not very good. And also because, you know, the volume is really underestimated, so I would say that this is not a good simulation. But if you are interested in simulating the low flows, and you extend this comparison and you check that indeed the low flows are well reproduced, you might be satisfied. Let's look at another graphical technique. Is a scatter plot of observed versus simulated discharge. In this graph, which should be depicted by using a similar extension for the two axes, a similar length. This graph is very useful. First of all, you have to use the same scale, meaning the same maximum number for both axes. And if you do so, a perfect simulation is given by the 1-1 line, the 1-to-1 line, the line with slope equal to 45 degrees. And of course, you don't get a perfect simulation in any case, but by looking at the displacement of the points around the 1-1 line, you get an idea of where the model is failing and where the model is performing well. In this case, you see that the error in the reproduction of the high flow is not much relevant, while you get a strong dispersion here, around here, for low flows. So this picture is extremely useful, and more useful than hydrograph comparison. Because if you compare the hydrograph for, let's say, 10 years, you can't distinguish any more the details. like in this case, even if you have 1 million of points, you can still distinguish the details. The points go one over the other, and therefore the picture is still clear. This is a kind of check that is often requested by scientific journals. They ask explicitly to you, please show me scatter plot observed versus simulated. In this case, again, I would say that the simulation is not really the best. It's, you say, okay, if you can't do better, it's fine, but it's not a good simulation. You see here, even for high flows, here we have 120 of observed versus 200 simulated in this point here. So it's a big mistake, big error. And even here, there are points with an error of 30 cubic meters per second. So 30 for low flows. If in percentage terms, this is 10 times. I think this is, yeah. This is comparison between flow duration curves. And what are the flow duration curves? Okay, let me postpone to tomorrow because it takes too much time, okay? But let me show you the final slide, sorry. And tomorrow I will get back this one. What is a good model? Let me give some indications. It's difficult to say. As I anticipated, it depends on the type of application. But I would like to give you some first hints to build your experience. The Nash efficiency usually of a good model stays between 0.6 and 0.9. Difficult to get Nash efficiencies above 0.9. I'm talking about validation, but even calibration. You can, but of course with the calibration you expect better performances. But in any case, both calibration and validation higher than 0.9 is very difficult. If you get 0.9, you must be very satisfied, even if it is in calibration. Lower than 0.6 means that really the model from a technical point of view is not much useful. The correlation coefficient, let's forget about it, but in any case, this is the range of good values. I won't ask you about correlation coefficient, it's just for your information. Mean relative error, this is important, in the range 15–40%. This is the range of useful models. If you get an error which is more than 40%, you understand that it's a very significant error. It's almost impossible for you to go below this limit of 15%. It's very difficult. Only ideal situations. Mean relative error in the simulation of peak flows, if you just concentrate on the peak flows, I would say 10–25%. This is restricted with respect to this interval here, because on the peaks, in percentage terms, your error is less relevant, because the peak is higher, the current flow is higher. And then, no evidence of significant model structural inadequacy for different river flow regimes, meaning that if you look at droughts, if you look at peaks, you get performances that are acceptable in any case. If you look at winter, summer, fall, you don't see evidences of significant inadequacies, clear inadequacy. Okay? These are some just basic information. And then tomorrow I will go back to this previous slide because I need to, probably you already remember what is a flow duration curve, but I think it's better if I